We are live. Welcome back. So, as you guys know, I have been gone for some time. It has been a long while. However, I'm back. And this is a new setup. We're going to be talking about homeostasis and fluid balance today. This is a setup inside of my apartment. I'm in my bedroom, actually. I'm on my desk. I have two monitors set up and everything. I have a little webcam, and I have this digital tablet, so we're leveling up. Same old microphone, same old me. Not much has changed, but if you guys like this sort of style of video, let me know. I might do it more often. I like doing it this way. It's currently, I don't know what time it is. I can't see it on the screen. It is currently, hold on. I'm still getting used to this setup. 6:20. It's 6:20 p.m. All right, so if you guys like this, let me know. And if you guys, as always, need more resources for the MCAT, please check out the links in the description. I have a new lecture email, lecture series sign up email thing. I have a new email list for my lecture series because, as you guys know, if you've watched the lecture series before, you know that the 2023 to 2024 lecture series ended in April. Now, the 2024 to 2025 lecture series is beginning in August. If you would like updates about how the lecture series is going, what I'm doing, what I'm teaching, things like that, please feel free to sign up in the link in the description below, and I hope to see your email there. And also, guys, this is a new format. Leave comments, what you liked, what you didn't like. If this is your first video ever, tell me what you like. And please do tell a friend. So with that being said, let's hop straight into the business. Now, fluid balance is something that MCAT students have always had a little bit of difficulty wrapping their heads around. And don't get me wrong, I had a little bit of trouble getting around it as well at first. But once you break it down into its sort of simplest terms, it's really not that bad, right? So there's necessarily a couple things that we have to start with, right? Some foundation, some sort of, cleaning up our foundation, our baseline, right? Now, what is this tube I'm drawing right here? Well, first of all, you know that this sort of equilibrium sign, I mean that something's going in and something's coming out. Well, what is that something? That something is fluid, right? So the fluid balance that we're talking about is the transition of fluid between these two compartments that we see. So inside this tube and outside the tube, correct? So inside the tube and outside the tube. I realize you guys now can't see the mouse, but I'm going to try to use that laser pointer whenever I can. So inside this tube and outside this tube. Well, what is this tube? This tube is actually the capillary, right? This tube is the capillary. And what is a capillary? Well, that's a very good question. I'm glad you asked, right? So you know that blood pumps out from the heart, and from the heart it pumps out into the largest artery, the aorta, right? And the aorta turns into the large arteries, and the arteries turn into the arterioles, which high yield fact, these cause the most resistance inside the body, the arterioles, and the arterioles actually turn into the capillaries, right? The capillaries. And then the capillaries transition into the venules, and the venules turn into veins, and all veins lead to Rome. No, they don't. They lead to the vena cava, and the vena cava leads back into the heart, right? And we went over this in our lecture about circulation, right? The circulatory system. All right. So we're looking at the level of the capillaries, right? After the blood has traveled all that way, we're looking at the level of the capillaries. Now, going back to our friend the capillary, since the blood is traveling through the capillaries, we can say that the capillaries are full of blood, right? And everything that comes with blood. Blood. And I'm going to put blood in parentheses. Well, why did I put blood in parentheses? Because blood isn't really just blood, right? Well, it contains blood, right? And this blood is made up of components. So first we have red blood cells and white blood cells, and we have platelets, right? And then what else do we have in the blood? Well, we have some ions and sugars and amino acids and proteins. These are like the molecules that exist inside the blood, right? So we have cells and we have molecules. And also blood is made up of water, correct? Water, which is of course another molecule, but not like these, right? So all of this stuff, the cells and all of these sort of ions, sugars, amino acids, proteins are dissolved inside the water, and that's what makes up the blood, right? So the water kind of acts as a solvent, and then everything else is a solute. And this becomes important when we talk about these things right here, right? Because these molecules kind of act as solutes, And when you have an increase in them, you increase the solute per solvent, which is actually just an increase in the molarity, right? And that increase in molarity is what we call, so if you increase any of these, you'll increase the osmolarity, right? The osmolarity. My handwriting's still not good. It's been months. Oh my God. So if you increase any of these guys right here, and I know you can't see it, I'm not pointing yet. If you increase any of these guys right here, you're going to increase the osmolarity, and that becomes important when we talk later. Now, let's take a look at this blood inside this capillary. Do you guys remember, if you watch the video on respiration, when I told you take your two hands and cup them and leave a space between them like this and try to generate force inside that space? Or sorry, not the respiratory lecture, the cardio lecture. Try to generate force inside the space. Like squeeze your hands together, no force is going to be generated. But if I pop this candle between them and now I push my hands together, I can generate a lot of force against this candle, right? Why is that? Well, you need something to push against in order to make force because it has to push back. Like think of the example of a water bottle, right? So if you have a water bottle and this water bottle has water inside of it, the water is pushing against the walls of the container. And when a fluid is inside a sealed container, it generates a pressure, right? So fluid in a sealed container generates pressure. Fluid inside a sealed container generates pressure. What is this pressure called? This pressure is known as the hydrostatic pressure. The hydrostatic pressure, right? And in biology, we denote this with a capital P, right? Now, the more water you have, the higher the hydrostatic pressure. That makes sense. In order to, hydrostatic pressure is one of the types of pressures that we see inside this sort of homeostatic balance. The other type of pressure is the one that students have a little more trouble, understanding. This is osmotic pressure. Let me do this in a different color, right? Because we're going to look at this in depth later. Let's look at osmotic pressure, right? Or sometimes you'll see oncotic pressure, right? Osmotic pressure is basically a sucking pressure. Right? I don't know if it was like my school that did this because a lot of the students that I asked didn't do this. Did you guys ever do that experiment in bio where you had like a membrane, right? You had a membrane and it was tied off at both ends. And then you put a solution of salt inside of here. So inside this membrane is 0.5 molar NaCl, right? And then you took this membrane, you tied it off at these ends, right? And it's loose, right? And then you take this and you put it inside of a container, right? So here's my membrane. And you put it inside of a container, and in this container is distilled water. So the water is hypotonic to the solution, right? Because it has less solutes. So what happens when you pull the membrane back out after 5 minutes? The membrane, it looks like this. Like it's super, super swollen and it's super tight and like so much fluid has gone inside of it. Why is that? Well, that's because water follows solutes, right? So when water sees this 0.5 molar NaCl and the concentration of NaCl here is 0, right? Water is going to flow in here to decrease that concentration, right? And that's exactly what osmotic pressure looks like. Osmotic pressure is the sucking force of solutes that pull on water from specific areas. So let me give you an example. Over here on this side, we have 0.67 molar NaCl. And over on this side, we have 0.45 molar NaCl, which means relatively we have more water to spare here than we do here. So the water is going to follow this way until eventually these level out, right? Until the molarities become the same. And this is a very, very common sort of idea inside of biology, right? So we see the same thing when we look at the kidneys. If you look at aldosterone, right, and how aldosterone works, virtual cookie, if you know this one, it actually increases the activity of sodium, potassium pumps inside of the distal parts of the nephron, right? And when that happens, the sodium gets pumped out more than the potassium, and that means that more sodium gets pumped out, which means that the water is going to follow whatever's moving more, and the water follows the sodium, which is why aldosterone helps to bring water into the body. If you didn't understand any of that, I am going to make a video about the renin-angiotensin-aldosterone system. Or you could go check out the homeostasis lecture in the biology playlist on this YouTube channel. All right, wonderful. So, if osmotic pressure is the sucking pressure inside of different solutes, you can imagine that when the osmolarity is high, that sucking pressure gets higher. Well, what does this all have to do with what we talked about in the first place? Let's zoom in on this guy, this capillary, right? So obviously this capillary is filled with fluid, right? And what color did I use for the fluid pressure, the hydrostatic pressure? It was blue. So the fluid inside the capillary, the blood inside the capillary, is pushing against the wall on the capillary and trying to force what? It's trying to force molecules of water out of the capillary, right? That's what hydrostatic pressure is doing. It's forcing molecules of water out the capillary. Because remember, this thing we're looking at right here, this sort of membrane right here is permeable, right? And in certain spaces, permeable to the water. It's permeable to the fluid, right? So this is known as what? It's a hydrostatic pressure, right? So we're going to call it P, and it comes from the capillary, so we're going to call it C. This is PC, right? The hydrostatic pressure of the capillary. All right, what about from the interstitium out here? And what is this thing called? I just gave it away. This is called the interstitium. Right, this is called the interstitium. The interstitium, it also has a hydrostatic pressure, right? And that hydrostatic pressure is known as PI, right? Or hydrostatic pressure of the interstitium, right? Not pi as in 3.14159, but pi or PI as in hydrostatic pressure of the interstitium, right? So you can imagine fluid exists here and it's pushing out, and if this sort of force gets high enough, the fluid gets pushed out, right? And the same thing over here, this fluid over here, and it's trying to get in, and if the pressure gets high enough, it gets in. But under normal conditions, PC equals PI, which means that the rate at which water escapes here is the same rate at which water gets in here, which is why there's no change in the volume, right? If there was a change in the volume, we'd have a problem, right? We'd probably be dead. Anyways, now, let's talk about osmotic pressures. We know, or I know, I hope you know, that there's solutes all in the blood, right? And there's solutes all in there's solutes all over the body, right? The solutes inside the blood, inside the capillary, are going to suck water in from the interstitium, right? This is known as the osmotic pressure of the capillary. And solutes inside of the interstitium right here are going to suck fluid out of the capillary, and that is called oncotic pressure of the interstitium, right? So we have oncotic pressure or osmotic pressure of the capillary and oncotic or osmotic pressure of the interstitium, right? So that, and normally, under normal conditions, pi c equals pi I, right? Well, if PC equals PI and pi c equals pi I, let's take a look. Let's take a look at what we got going on, right? If PC equals PI and pi c equals pi I, right? And pi I comes into the capillary and PI comes into the capillary, and then PC goes out of the capillary, right? Oops, hold on. Retrack. This is how confusing it gets. Whenever I do this, I draw it out, right? So here's PC, hydrostatic pressure in the capillary, forcing water out towards the interstitium. Here's PI, the fluid that's pushing into the capillary. And then the sucking force is going to come from the solvents in the capillary, so that's going to be pi C. And then the sucking force this way is going to be pi I. Well, PC plus pi I equals your outs, right? And in the body, your ins always have to equal your outs. Pediatrics taught me that, right? So these are your outs, these are your ins, and they must be equal. All right. Now, what happens when this balance gets thrown out of loop? Well, how does the balance get thrown out of loop, right? How does the balance get thrown out of loop in the first place? I actually wrote some notes that we're going to go through, right? We're going to go through these different sort of examples. And the first example we're going to go through is the gym bro. The gym bro. Everyone loves the gym bro. And gym bro is telling you, yo, you should, and I want you to take notes. I want you to take notes. This is what you have to write. You should totally eat some salt before your workout. Pump is insane. Looking like Ziz out here. Right? I was a gym rat at some point. I have no shame. Right? Well, why? Why is the pump insane when we ingest salt? Take a second to think about it. Pause the lecture. Think about what the salt does when you ingest it. Where does it go? Where does it end up? And how does it relate to what we're talking about? Pause this lecture. And if you didn't pause the lecture, I'm still going to give you a little bit of time to think about it. All right, that's enough time. So what does ingesting salt do? Well, salt, what is salt, right? Normally salt is just, shout out Jimmy Neutron, is sodium chloride, right? So the salt is eventually going to go into the stomach, right? And into the GI system and small intestine, blah, blah, blah. And it's going to get absorbed, and it's going to get absorbed into the bloodstream. Now, if you have sodium splitting up into sodium and chloride, right? These are what? These are ions, and that means that these are solvents, or sorry, solutes. And solutes are actually going to increase the osmolarity of the blood. Right. Now, if the osmolarity of the blood increases, let's take a look back at our guy over here. This is basically the osmolarity. These are all the solvents inside the blood, solutes inside the blood. So these are the I keep messing that up. Oh my god. These are all the solutes inside the blood, the things that are dissolved inside the blood, right? But if these go up, that means the concentration here is higher than the concentration here. And now the water wants to lessen the concentration inside. So fluid flows into the capillary. And what is that? That would be an increase in pi c. How? Well, osmolarity or osmotic pressure is all determined upon this concentration of solutes inside of that compartment. So if the solutes inside the capillary go up, pi c is going to go up. It's going to win the fight over pi I, and water is going to flow into the capillary from the interstitium. Now, what does that have to do with little old Jimbro over here, right? Well, let's write a little diagram. So, salt leads to increase in osmolarity of the blood, which leads to increase in pi c, which leads to increase fluid, increase fluid, I don't know. I don't know the word here. Increase fluid transition, I guess. Or increase fluid movement, right? I guess the correct word would be displacement. Increase fluid movement into capillary. Because remember, when you increase the solutes, it gives you that sucking force on the fluid anywhere else. Right, so this is why the pump is insane. Because you're taking the fluid from outside the capillary and pulling it into the capillary and back into the veins and everything like that, and you effectively increase the blood volume. This is another way that chronic increases in salt intake can actually lead to hypertension, right? Let's talk about the next case. I hope that made sense. And if it doesn't make sense, I know I'm not in front of an audience right now. Please just leave comments and please just leave questions in the comments. I will get back to them whenever I can. I do try to read all the comments. Some of you guys leave the nicest comments in the world. It makes me feel so welcome and so. Sorry guys, long day of treating sick babies. But it makes me feel so warm inside. It makes me feel like I have a community here on YouTube. So thank you guys so much for your continued support. Seriously, it means the world to me. All right. What about dehydration? What does dehydration do in this whole thing? Well, dehydration is a loss of water. And whenever we're talking about water and not the solutes, we're talking about hydrostatic pressure, right? Hydrostatic. Well, dehydration is first going to pull water from the blood, right? We're going to decrease the circulating blood volume of water. And if the blood inside the capillary is what we're worried about, we're looking at a decrease in the hydrostatic pressure of the capillary. Well, let's go back to our diagram right here. Let's go back to our diagram right here. And we see that hydrostatic pressure of the capillary is what's keeping fluid out this way. if this gets knocked down, right, and this doesn't, or if PC just decreases relative to PI rather than them being equal and having equal rates, then PI is going to overwhelm and fluid is going to move into the capillary from the interstitium, right, in order to keep the concentrations as they should be. This is all about keeping concentrations inside of the capillaries as they should be, if you haven't gotten the gist, right? So this is going to lead to a flow of fluid into capillary because PC less than PI. And remember, PI comes into the capillary. The hydrostatic pressure of the interstitium. Because now, think about it. There's relatively more water, more fluid in the interstitium than there is inside the capillary. And since there's relatively more water inside the interstitium, it can donate that down to the capillary, and that's why PI forces the fluid into the capillary. Two more examples, and I will give you some examples from medical school right now. So the first example from medical school is liver failure. You can put your pens down. You don't need to write this. But the liver actually produces albumin, right? And albumin is a very important protein inside your body. For the MCAT, you do maybe need to know that steroid hormones can circle around the body attached to albumin because they're nonpolar. They're not able to be solubilized inside the blood. So the liver produces albumin, and when the liver fails, so liver failure leads to decreases in albumin. Well, this decrease in albumin actually is one of the ways that we can decrease the oncotic pressure of the capillary, right? Why? Because we have less osmolarity. When we have less molecules inside the blood, we have less osmolarity. The water is less drawn towards those molecules, right? So let's look back at our diagram right here. If we have a decrease in pi c, right? If we have a decrease in pi c, that means that what? If we have less solutes over here, the concentration of solutes over here is going to go down, which means the relative concentration of solutes over here is going to go up. And if the relative concentration here is high, the water is going to prefer to go that way. All right, now what does this mean for our due to liver failure? Well, this normally happens when what? This normally happens when people are alcoholics, right? So the increase in the PI, or the pi, which is going to draw fluid out of the capillary, is going to leave fluid inside of the interstitial space. And this is what you see as edema. You'll realize that a lot of people who are alcoholics have fluid in their legs, fluid in their abdomen. They look very puffy, very big, right? And they're heaving and huffing and they're carrying a lot of weight. Is because of all this fluid that's escaping out because of their low albumin. Okay, wonderful. And I said 2 more cases. I actually lied. That was it. I hope you guys like these sort of short forms of videos a little more. They're a bit more digestible. I'm going to get more into making videos like this. Also, if you guys want to support the channel, you don't have to. I do have ads now on YouTube. Funny story about that. So at first, I didn't want ads on my YouTube at all because I wanted students to be able to watch my lectures without getting interrupted, right? But then one of my students messaged me. He's like, "Bro, I love watching your lectures, and I watch every single ad that you put up." A lot of people have messaged me that actually. They're like, "I watch every ad. I want to make sure you're making the money." But this was before I actually knew that there were ads on my videos. I didn't think there were, right? And I was like, "Wait, there are ads on my videos?" And they're like, "Yeah, there's like one every 10 minutes or so." And I was like, "That's strange." So I reach out to YouTube, right? And then I was just like, "Oh, well, are there ads on all videos?" And they're like, "Yeah." And I was like, "Do I make money off of it?" They're like, "Not if you don't apply to do so." And I was like, "Okay, well, if the ads are going to be there anyways, we might as well make the ad revenue off of the video." So that's what we do. And now I make a little bit of ad revenue off of YouTube. It's very, 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 like, it's, it just humbles me so much. Like, I'm at a loss for words that I can make money on this online platform, just teaching people and doing exactly what I love. But we're going to continue to donate some of that to charity. So I hope I can send you guys, if you guys sign up for the email list and the lecture series email list, I always send out the receipts to all my donations. And also, if you guys would like to donate personally to the channel, it is never, ever, ever an obligation, ever. It is not something that you're obligated to do, but 50% of all donations to either the Buy Me a Coffee page or my Venmo in the description below goes towards charity as well, and I send out those receipts on my lecture series email list. So please join the lecture series email list if you would like to stay updated on what we do when the lectures are restarting. I'm going to send it out. It will be for the 2024 to 2025 year. So if you were on the lecture series list, the lecture series email list for last year, and you still want to be on it, you can sign back up using the link that I'm going to put in the description. It'll be the first link in the description, how to sign up for the email list. And if you'd like to support the channel and donate a little bit to charity, feel free. Guys, thank you so much for watching. It is so good to be back. I love this new format. I love it. Let me know what you think. I know the handwriting's a little bit iffy, but thank you guys so much for all your continued support. And I hope that I am able to be an asset to you. I hope I'm able to be as beneficial to you as humanly possible. And refer to a friend. Tell your friends all about my lecture. I hope I've been very helpful. Thank you guys, and I'll see you in the next one. Bye-bye.